Hey guys, welcome back. Yeah, it looks like we're going to be here for a couple more weeks at least, so we're going to try and knock out parallel circuits today. And look, I just want y'all to know I really appreciate the response that I've been getting from y'all. It's been really great. Just stay in touch, and if you have any questions, I'm getting to them as quickly as I can. So I appreciate the patience. So anyway, today, we're going to introduce parallel circuits. First thing I want you to know about parallel circuits is they're totally opposite from series circuits. I told y'all that there were two ways to hook things up. You can either hook them up end to end or side by side. Now we hooked up the end to end connection. We call that series. And what we found out about series circuits is because we hooked them up end to end, it only created one path of current flow. And because there was only one path, the current everywhere was the same. And then the applied voltage was divided up amongst the individual components that are connected in series. So that being said, along with the resistance of being simply added up, we're going to talk about parallel circuits, and those are side-by-side connections. Even the connection type is opposite, end to end and side-by-side. So in a parallel connection, that's the first thing that I want you to know, is that it is a side-by-side connection. Okay, so with a side-by-side connection, the first thing that you realize is that now there is more than one path of current flow. And as we can see, if current is flowing in, and this is a key point, look for junctions where current will flow in, and what's going to happen is because of more than one path of current flow, because of the side-by-side connection, this current is going to split up. So the first thing you need to know is there's going to be more than one current, or like in series, voltage divided, in parallel, current's going to divide. So a side-by-side connection because there is more than one path of current flow. So parallel circuit, side-by-side connection, this causes currents to divide because now we have more than one path for current to actually flow through. So that's the first basic concept you need to lock in on when it comes to parallel. Now, just as these currents come in and split up, as they flow through, they come back out to be the same amount of current that went in. You can't get out more or less than what you put in. You got to get the same thing out, and it will always split like that. Not in half, like the voltages that we talked about in series, but these currents divide proportionally based on the amount of resistance. So parallel circuits, side-by-side connection, creates more than one path for current, which causes current to divide. So that's important. Current divides in a parallel circuit. Well, how about voltage? Well, again, we got to remind ourselves what voltage is. Now, voltage is the difference of potential between 2 points. So voltage is the difference between 2 points. So if I have a source, we'll say it's a 10-volt source, and that 10-volt source comes out to here, and the negative side of that source comes out to here. If I've got 10 volts applied from that source, how much voltage will I have at these 2 points? Well, voltage is the difference between 2 points. I'm going to have the same voltage. I'm going to have 10 volts between these 2 points. These 2 points are connected directly to my source, so my source is 10 volts. I'm going to have the 10 volts between those 2 points. Now here's the deal. If I were to connect a resistor from this point to this point, how much voltage would I have across that resistor? Well, the same 10 volts that I have between the 2 points, because I connected the resistor up to the 2 points. And look, even if I have another resistor, and it comes down, and it's connected also to those same 2 points, since voltage is the difference between the 2 points, and I'm connected to the same 2 points, well, the voltage across each one of these resistors will be the same. The voltage across each one of these paths that the resistors are in will be the same. If I got 10 volts from this point to this point, and I hook up a resistor from that point to that point, I'm going to have 10 volts across it. Even if I hook another resistor up to those same 2 points, I'm going to have the same 10 volts across that path. So voltage being the difference between 2 points, and if I'm connecting components up to those 2 points, I'm going to have that same voltage across each one of these paths. So unlike in series where current was the same, here in parallel, voltage will be the same. So that's the next point. Current divides, more than one path. All the paths are connected back to the same 2 points, so the voltage across each one of these paths is the same. So current divides, and voltage is the same. Okay, so current divides and voltage is the same. Now, excuse me. The next thing we have to talk about is resistance. And what I'm looking at doing is I'm probably going to break this into 2 videos. First the introduction, and then the analysis part. So the next thing we have to talk about is resistance. Now, in series, when I had resistors that were in the same path, their resistance accumulated. Or in other words, we simply added up the value of resistance. Well, that's not the same now, see, because I'm not adding another resistor in the same path. I'm actually adding a new path that just happens to have a resistor in it. And there's a difference, see, because a path allows current flow. You think about this. If they open a new lane on the interstate, the overall flow increases, which means the opposition to the flow had to decrease. I know that's kind of freaky, but think about it like this. If they open another lane, the amount of time it takes you to get home is actually going to be less, more lanes. And so this is the concept that we're talking about. Now, resistance is the ability to oppose current, the opposition to current flow. Well, we're not putting more opposition. We're actually adding more ability to allow current by adding extra paths. We're adding the ability to allow current. And believe it or not, they have a name for this ability to allow current. The ability to allow current is called conductivity or conductance. Conductance. The ability to allow current. And conductance, we can consider it as the opposite of resistance. The ability to oppose current, the ability to allow current. The ability to oppose current, resistance, the ability to allow current, conductance. Okay? So it is the opposite of resistance. Okay? The opposite of resistance. Conductance has a letter designation. And the letter designation for conductance is G. I don't know where they get stuff, but the letter designation for conductance is G. And the unit of measure for conductance is the Siemens. You may have heard of the company Siemens. It's a big electrical distribution company. That's where they get it. And the symbol, yeah, it's IE. Just look funny. The symbol is a lowercase g. Okay? So conductance, the ability to allow current, is the opposite of resistance, and it has a letter designation of G. And the unit of measure is the Siemens. It has the small symbol, the letter G. Okay? Now, let me tell you why I told you that. And y'all should know by now that I'm flipping through this, so pause it, write the stuff off the board, and then continue on with the video. So current divides voltage is the same, and we just mentioned this thing called conductance, the ability to allow current flow. And we said it was the opposite of resistance. Now, you know we deal with numbers, and what we're talking about when we find the opposite of a number, how do we find the opposite of a number? Well, we invert it. See, in reality, the value 2, and we talked about this, the value 2 is actually an improper fraction, 2 over 1. Now, if I wanted to find the opposite of 2 times, I just flip it over, or I put a 1 over the value. Now, this is important because this is how we convert resistance into conductance. We use the 1 over key on the calculator. Now, if you look at your calculator, if I can see it, just above the EE key is your 1 over X key. That's going to be your new friend, believe it or not. So keep that in mind, the 1 over X key above the EE key on your calculator. Now, so to find the opposite mathematically, we invert it. So same applies to the actual resistance. If I know the resistance and I want to find the conductance, if I want to find the conductance and I have the resistance value, all I'm going to do is 1 over that resistance value. Now, if I want to turn around and find the conductance value, or the resistance value from the conductance value, again, it's the opposite, as resistance is equal to 1 over the conductance. All right? And that's a key point to lock in on when we talk about this resistive nature in the circuit. So look. And we're going to keep this one simple. So I want you to think about this. Okay, so if I have a 10-volt source, and R1 is a 10 ohm resistor, right now, with this circuit the way it is, with just the one resistance and the one source, I can determine my current flow. Well, at this point, my total resistance is equal to 10 ohms. So RT equals 10 ohms. And if my total applied voltage is 10 volts divided by that 10 ohms, Ohm's law, will give me my total current of 1 amp. Okay? 10 divided by 10 is 1 amp. So here we go. That's all fine. Right now, total resistance is 10 ohms. Total current is 1 amp. Now, what happens if I hook up another resistor on the side of that one? And let's say R2 is a 5 ohm resistor. Okay? So now, I got a 10 ohm resistor and I got a 5 ohm resistor. Well, do I have the full 10 volts still across R1? Well, yeah, I do. It's hooked directly to the 10 volt source. And the question is do I have the voltage across R2? Got the full 10 volts there too, because R2 is directly connected to that source. So if 10 volts is across 10 ohms, Ohm's law says I still got my 1 amp of current flow. But now, looking at it over here in R2, I got 10 volts and a 5 ohm resistor. So 10 volts divided by that 5 ohms gives me the 2 amps. Okay, now I got 2 amps coming through R2. Still got the same 1 amp going through R1. Now the question becomes, my total current coming out of the source, how much current do I have to have coming into this junction point right here to give me 1 amp up through R1 and 2 amps up through R2? 3 amps, right? 3 amps coming in, split up. 3 cars came into a subdivision. 1 car went that way. How many cars went that way? Well, the other 2 went that way. So now, what happened to my total current flow? Well, my total current flow, because I added another path, increased up to 3 amps. So what does that mean as far as my resistance goes? If my current went up, my voltage stayed the same, my resistance had to go down. It had to have gone down. Well, let's see what it went down to. All right, so if I'm looking at this, I'm going to take and find my new total resistance by taking my voltage and divide it by my new current flow. 10 volts divided by 3 amps gives me 3.333 ohms of total resistance. With a 10 ohm resistor and a 5 ohm resistor, now my total resistance is only 3.333 ohms. Well, how is that possible? Well, I'm not adding resistance. I'm adding conductance. I'm adding conductance in this circuit. And so if I want to find the conductance of these resistors, let's see. All right, so I'm going to take the 10 ohms, that's the first resistor. I'm going to enter in 10 ohms, and I'm just going to hit the 1 over X key. And that tells me that I have 100, and it's to the negative third, which is milli. Since I'm finding conductance, it's millisiemens. So I took the resistance, I 1 over X it, and I got 100 millisiemens conductance in this path with R1. Same thing over here with R2, I'm going to find the conductance because that's what I'm really adding up. So I'm going to take that 5 volts, hit my 5 ohms, hit my 1 over X key, and I get 200 millisiemens. So now, over here with the 5 ohms, half the resistance gives me twice as much conductance. And so in parallels, we're actually adding conductances. So we're going to add this together to give me a total conductance that's equal to 300 millisiemens. 100 millisiemens plus 200 millisiemens gives me the 300 millisiemens. Now this is total conductance. I don't want total conductance. I need total resistance. So how do we convert conductance back into resistance? Well, we hit the 1 over X key. I told you the 1 over X key is your buddy. And so we're going to take and add that 100 millisiemens to it. I get my 300 millisiemens. Now I'm going to come over here and hit my 1 over X key. Boom. What does it give me? 3.33 ohms of resistance. The 3.333 ohms of resistance that I knew I had in there in the first place. So what do we do to do this? Let me show you. So we took the resistance of R1. We 1 over X it. We took the resistance of R2. We 1 over X it. We added these together, and then that gave us total conductance. So we took all of that and 1 over X it again. So here's the key, the resistance formula in parallel. Total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is how we go through and we find the resistance in a parallel circuit. We add them up what I call the 1 over way, the reciprocal way, but the 1 over way. Series, we add them up regular. Parallel, we add them up the 1 over way. Okay? So let's say we have these resistance values, a 300, a 200, and a 500 ohm resistor in parallel. This would be the key sequence in order to find the total resistance. So what you'd do, you'd enter in the 300 ohms, hit the 1 over X key, plus the 200 ohms, hit the 1 over X key, plus the 500 ohms, hit the 1 over X key, equal it all up, and then at the very final step, you hit that 1 over X key one last time. So 300 1 over, that gives me the conductance, plus 200 1 over the conductance, plus 500 1 over the conductance, and I equal it all up. That gives me total conductance, and then I have to 1 over X it one last time to convert it back to resistance. All right? So run through this a couple of times. Make sure that you got that 1 over X key. Remember, if I've got kilo ohms or mega ohms, I have to enter in the exponent, 3 or 6 or whatever I've got. And look, if you come out with an answer in milli anything, -6, -3, milli micro, if you come out with a negative exponent at the end, what that means is you forgot to hit that last 1 over X key. Okay? So if you get a milliohm, don't write it down because it's not correct. Hit that 1 over X key that last time, and it converts it back into that total resistance. Okay? So just to rehash the deal about parallel circuits. More than one path. Current divides into the multiple paths, and all the individual currents add back up to that total current. All the individual currents will add back up to that total current because that current just simply divides up like a pizza. And if I put all the pieces of pizza back together, I end up with the pizza. Same deal as voltage in series, we have current in parallel. Okay, so what does the voltage in parallel do? That's right. Voltage stays the same. Again, voltage is the difference between 2 points, and I don't care how many paths I have hooked up between those same 2 points. The voltage across each one of those paths is going to be the same. And then last but not least, remember, focusing in on the big three, voltage, current, and resistance. Currents divides, voltage is the same, and to find total resistance, we add them up the 1 over way. Or RT equals 1 over R1 plus 1 over R2 plus 1 over R3. However many resistors I have in parallel, just keep chunking them on the end. Just remember to hit that last 1 over X key. Okay? All right. So that concludes the introduction. On the second video, I'm going to go through some analysis problems, show you how to analyze these. I'll put all the formulas on the board to freak you out again. But look, just remember, it's nothing but Ohm's law. This is the new formula here, and then everything else is just straight up Ohm's law. Finding voltages and currents, you divide or multiply. Okay? So parallel circuits, more than one path, causes current to divide, and the voltage is the same across each one of them. And to find total resistance, I add the resistors up the 1/way. Okay? So that concludes this video. The next one will have the analysis and the problems that you need to work to get your attendance. Sure appreciate you, folks. Y'all hang in there. We're going to make it through this. All right.